Alright, so in this video we're going to take a look at another gas law, which is referred to as Dalton's law of partial pressure. This is a law that becomes very important when we're talking about mixtures of gases. For example, if we're talking about air, air is made up of nitrogen and oxygen, carbon dioxide, some other gases. So if we wanted to talk about each one of those gases individually, each of those gases contributes its own pressure towards the total pressure that we have in the atmosphere. And so that's what Dalton's law takes a look at, is how to figure out the difference between the total pressure that a sample of gas produces compared to the pressure that each individual gas within that sample contributes. And so to do this, the total pressure is equal to the sum of all of the partial pressures, where the partial pressure is the pressure that that gas would exert if it was the only material within that container. So in other words, within that volume and at that temperature. And so we end up with this equation here, where P total is equal to P, the partial pressure of gas 1, plus the partial pressure of gas 2, plus the partial pressure of however many gases are present within that sample. So if we take a look at a problem here, we can see, for instance, that we know that we have a mixture of gases, and we have three gases here, gas A, B, and C. And they also give us the partial pressure for each of those gases, and they want to know what the total pressure is going to be. So to solve them for that total pressure, we simply add the pressure of gas A to the pressure of gas B to the pressure of gas C. And plugging in those values that we know A is contributing a pressure of 256 millimeters of mercury. Gas B has a pressure of 345, and gas C has a pressure of 127. And so adding these three numbers together will get us our total pressure, which ends up being 728 millimeters of mercury. And so if you were to measure, for instance, the pressure within that flask that these three gases were occupying, you would have a total pressure of 728 millimeters of mercury. We can also use this equation to help us solve for the partial pressures if we know the partial pressures of the other gases and we know the total pressure that sample of gas is exerting. So take a moment, try to complete the next question on your own, and then we'll come back and take a look at the answer. Alright, so this is what we should have gotten here. So we know that our total pressure that the atmosphere is going to be exerting is equal to the pressure of nitrogen plus the pressure of oxygen plus the pressure of carbon dioxide plus the pressure of all the other gases that make up the atmosphere. This time we plug in the values that we know, and we recognize that the unknown is one of our partial pressures. So in order to solve for this, we would be subtracting each of our partial pressures that we do know from the total pressure, leaving us with nitrogen's partial pressure being 191.3 kilopascals. Here is another type of question that you guys may come across. In this question, if we take a look and read through here, we see that it's looking for partial pressures, and then it wants to go on and have us calculate the total pressure. But when we actually read the given information, we see that we have volumes, we have a temperature, and we also have some grams. And hopefully what we recognize is grams are a way for us to get to moles. So I have a volume of 2.5 liters, I have a temperature of 22 degrees Celsius, and I'm looking for a pressure, and I also know ultimately number of moles. And so the equation then that we would be using here is going to be the ideal gas law, PV equals nRT. And so the first thing I'm going to have to do is figure out what my N values are. So let's start with xenon. I have a mass of 2.57 grams of xenon, so I'm going to go ahead and put that over 1. And then, setting up dimensional analysis problems, grams of xenon is going to go in the bottom. I want moles of xenon, they're going to go up top. And since this is my molar mass, looking to my periodic table, 1 mole has a mass of 131.29 grams. Leaving grams to cancel, and I am ultimately left with 0.0196 moles of xenon. Whoops. So take a moment, convert the mass of nitrogen and the mass of oxygen into moles, and then we'll take a look at how to do the rest of the problem. Okay, so if we take a look now, I see I have my moles of each of my gases. I have my volume and my temperature, which I can get into Kelvin, and 22 degrees Celsius is 295 Kelvin. Pressure is what I'm looking for, so now I need an R. Since my question doesn't specify which R value I need, I can go ahead and pick. I'm going to go ahead and do mine into atmosphere, so I'm going to be using 0.0821 liter atmospheres per mole Kelvin. And so now I'm ready to go ahead and plug my values into my equation. So the first thing I'm going to do is try to find the partial pressure that each gas exerts. So in order to do this, I'll be using the volume and the temperature that the gases are at, and the number of moles for each individual gas will be plugged into this equation one at a time. So starting with xenon, we are looking for our pressure at a volume of 2.5 liters, and we have 0.0196 moles. Using our R value, and our temperature of 295. And at this point I can go ahead and solve for pressure, so I'm dividing both sides by 2.5 liters, leaving me with a pressure for xenon, where moles cancels, liters cancels, Kelvin cancels, left with just atmospheres. And plugging that all into my calculator, we should end up with 0.19 atmospheres for xenon. Right. Now I'm ready to move into the next portion of the problem, where I find the partial pressure then for nitrogen. Again, using the same volume, temperature, and R value, but this number of moles. So take a moment, complete the number or the pressures for nitrogen and oxygen, and then we'll take a look at how to find your total pressure. Okay, so now that you've found the pressures for each individual gas, we're ready to find the total pressure. Now I'm kind of running out of room here, so we're going to go ahead and write this up top here. But our total pressure is going to basically be the pressure of xenon plus the pressure of nitrogen plus the pressure of oxygen. And plugging those values then that I know in, we plug in 0.19 for xenon, we plug in 0.35 for nitrogen, and we plug in 0.31 for oxygen, which gives us a total pressure then of 0.85 atmospheres. So that would be the answer to your second question. So in this question we had to use a couple of different gas laws. We had to use both the ideal gas law and Dalton's law in order to solve for it. Now, why is Dalton's law going to be important for us? Well, one of the biggest places where we actually use Dalton's law is when we go about collecting gases. So if we were in the lab setting and I asked you guys to collect a sample of gas that you created or that was released, one way to do this would be to take a gas collection tube, which is basically a really big tube that's closed at the top and is open on the bottom, and you fill it with water. And then in that tube, you basically place it into a container of water, and then when the gas bubbles up into the tube, it fills the top of our tube and leaves us with a way of measuring how much gas is up here. So basically up here we have a bunch of our gas particles of whatever gas it was that we were interested in. So the gas that we wanted to collect is going to be up here. But the problem is that we don't just have the gas that we want to collect up there. We also have other gas particles up here. And these gas particles are actually water vapor. All right, so that's going to be our water vapor. So if we want to know what the pressure is within this gas tube that we've collected our gas in, we can't just say the atmospheric pressure, because remember, we're pushing down here, right? The atmosphere, or the gas in here is pushing down, and the atmosphere here is pushing down. So when these two forces are equal, we can say that the pressure inside of here is equal to the pressure outside of the room. We can't just say that the atmospheric pressure then is equal to the pressure of our gas. Instead, we have to recognize that our total pressure inside that gas collection tube is equal to the pressure of the gas we collected plus the pressure of the water vapor, where this water here has evaporated up into this tube a little bit. And so this then is how you would go about finding the pressure of just the gas that was collected. So for instance, the pressure total is going to be whatever atmospheric pressure is. And the pressure of water, it has to be a value then that we look up. So this value is going to come from a table like the one present right here. And so as you can tell, the amount of vapor pressure that you have is dependent upon the temperature that you're at. So if we were at approximately room temperature, which is more or less at 20-ish degrees Celsius, water vapor may be exerting a pressure of 17.536 millimeters of mercury. So if I wanted to know what the pressure was of my gas, I would have to plug my values into my table. If we were at sea level, if we were at 1 atmosphere pressure, or in other words 760 millimeters of mercury, the pressure of my gas then that we would be collecting would be equal to the pressure of that gas, plus the pressure of 17.536 millimeters of mercury, which gives us a total pressure then of our gas as equaling 742 millimeters of mercury. And so this is going to be a very important idea as we move into next week, where we will be doing a lab where you will actually be collecting a gas through water vapor, or through water displacement, and you'll have to account for the vapor pressure of water within your gas collection tube.